So we're going to now look at techniques for evaluating limits. So first example, let's determine the limit as x approaches -3 for the following function. So let's start by using direct substitution. And notice when using direct substitution, we get what's called the indeterminate form 0/0. And previously, in order to evaluate the limit, we would test values of x from the left and from the right to see what the value of the function is approaching. So we're going to look at a more efficient method when evaluating limits of the form 0/0. So in many cases, the limit cannot be found by using direct substitution. So there are other methods to evaluate a limit when direct substitution produces 0 in both the numerator and denominator. As mentioned, this is called the indeterminate form, and for such cases, we are going to look for an equivalent function for f of x. So let's go through some examples. So the example we just did. So the first method involves factoring. So we want the limit as x approaches -3. For this example, we can factor the numerator. So we get x plus 3 times x minus 2 all over x plus 3. Notice we can cancel out the factor of x plus 3. And what we're going to do now is evaluate this equivalent limit, x minus 2. And notice now if we use direct substitution, we get -5. So therefore, the limit as x approaches -3 for the function given above is equivalent to -5. The expression gave us 0/0, and we used a factoring method to find an equivalent expression in order to evaluate this limit using direct substitution. Second one we've seen previously. If you see a square root minus or plus some number or some term, we can multiply by a conjugate. So for this example, we're going to multiply by the root of x plus 1 in both the numerator and the denominator. So this gives us the limit as x approaches 0 of, if we multiply the numerator, I'm going to get x plus 1. The middle terms will cancel, and I'll get x plus 1 minus 1 all over x times the root of x plus 1 plus 1. And again, you do not need to expand the denominator for this example. So this gives us the limit as x goes to 0 of x over x times the root of x plus 1 plus 1. We can cancel out our x's. And now we're evaluating the limit as x approaches 0 of 1 over the square root of x plus 1 plus 1. Now we have an equivalent expression, and when using direct substitution, we're going to end up with 1/2. So this is the limit of our starting function. So this is the limit as x approaches 0 for our function, and it equals 1/2. If we see a root other than a square root, we can use the substitution method. So for the substitution method, we're going to let u equal the cubed root of x plus 8. So you're always going to let u equal the more complex function in the expression. So if u equals the cubed root of x plus 8, we can now isolate for x. We cube both sides, so we get u cubed equals x plus 8, and therefore we get x is equal to u cubed minus 8. So now we're going to sub those in for the following term. So there's my x, there's my u, and I'm left with the following expression. I'm left with the limit of u minus 2 over u cubed minus 8. The next part is, notice my function is now in terms of u, so I need to change this x approaches 0 into u approaches something. So to do that, what we do is we take this term here, and since x is approaching 0, we're going to sub 0 into that equation. Then u is approaching, well, we're going to sub 0 into our expression for u. So we get the cubed root of u plus 8. And therefore u is going to approach, the cubed root of 8 is going to be equal to 2. So u is approaching 2. And now you need to check this expression. And the way you can check it is using direct substitution with the value of u. So if we sub 2 into this equation at the moment, I'm going to get 2 minus 2, 0 over 2 cubed minus 8 is 0. So I know everything is correct. And now we go back to our first method of factoring to make an equivalent expression that we can solve using direct substitution. So we end up with the limit as u approaches 2 of u minus 2 in the numerator divided by, well, let's factor u cubed minus 8. That's equivalent to u minus 2, u squared plus 2u plus 4. Again, these terms will cancel out, and we're left with the limit as u approaches 2. I see I've made a mistake there, so that's u approaches 2, of 1 over u squared plus 2u plus 4. Now if we use direct substitution, I'm going to end up with 1 over 12. So again, this is the limit as x approaches 0 for our given function, and we see that it equals 1 over 12. So how did I factor that cubic function? For this example, you would need to know your difference of cubes factoring method and your sum of cubes factoring method. So for our sum of cubes, it's a plus b, and then times a squared minus ab plus b squared. And then for our difference, it's a minus b, then a squared plus ab plus b squared. So you might want to note the following shortcuts. All right, next one. Again, we've seen one similar to this. Basically, we have two fractions, so let's find a common denominator. So I'm going to multiply the first term by 2 over 2, and I'm going to multiply the second term by x plus 2 over x plus 2. And when we do that, we're left with 2 minus x plus 2 over 2 times x plus 2. And that's equal to negative x over 2 times x plus 2. So we're going to replace this expression with this expression. So now we're looking for the limit as x goes to 0 of negative x over 2 x plus 2 divided by x. Remember, that's x over 1. And that's equivalent to the limit as x approaches 0 of negative x over 2 times x plus 2. And then this is times now 1 over x, which is great. We can cancel out those two x's. And we're left with the limit as x approaches 0 of negative 1 over 2 x plus 2. Using direct substitution, we get negative 1 over 4. So therefore, the limit as x approaches 0 for our starting function is equal to negative 1/4. Now, one thing I forgot to mention with all these examples is that notice, if I was to sub in 0 initially for this example, I would end up with 0 over 0. Same thing with this example, I'd end up with 0 over 0. And that's why we're using these shortcuts. Same with this example. If I sub in 0, I get 0 over 0. And the first one, we already know that that was 0 over 0. All right, example number 5. What happens when we have the absolute value? Once again, if I sub in 2, I get 0 over 0. So this is our indeterminate form. So now we need to find the limit for this absolute value function using another method. And in this case, I'd set this up as a piecewise function. I would test the limit as x approaches 2 from the left and see what we get. And then I'd test the limit as x approaches 2 from the right. As we approach 2 from the left, that means I'm going to sub in a number just a bit smaller than 2. So the absolute value of, let's say, 1.9 minus 2. Normally that would be negative 0.1, and then the absolute value of that would be positive 0.1. So another way to think of it is this. Any number less than 2 will give me a negative number within the absolute value bar. So that means if I change the formula to this, negative x minus 2, that's the same thing as evaluating the absolute value for any number less than 2. And then we rewrite the bottom, and this is equivalent to the limit as x approaches 2 from the left. These cancel, and this gives me negative 1, which tells us that this limit is negative 1. What about if I put any number greater than 2 into this equation? Well, let's say I take 2.1 minus 2. Notice that is equal to 0.1. I don't need to change the sign. For any value greater than 2, I can rewrite this as x minus 2 over x minus 2. And again, I see that this is the limit as x approaches 2 from the right. These factors cancel out, and I'm left with the limit as x approaches 2 from the right of positive 1, which gives me that the limit is equal to 1. Notice the left and the right hand limits are not the same, so therefore this limit does not exist. Take note here, if an example does not involve any of the following methods, then we can still use an approximation method. So that means using a table, or if you have the graph, using the graph. Alright, last part. Properties of limits. So here are the following 5 properties that are important to note. If you want to find the limit of one function plus another, you can take the limit of the first function and add it to the limit of the second function. If you are finding the limit of a constant times a function, it's the same thing as evaluating the constant times the limit of the function. If you're finding the limit of 2 functions being multiplied together, you can find the limit of each independent and then multiply. Similar with dividing. And finally, if you want to find the limit of a function raised to an exponent, well, just find the limit of the function first and then raise it to that exponent. So let's see how these help. So example 5, use the limit laws and the graphs of f and g to evaluate the following limits if they exist. So notice the first one says the limit as x approaches negative 2 of f of x plus 5 times g of x. Well, using our limit laws, that's the same thing as finding the limit as x approaches negative 2 of f of x plus 5 times the limit as x approaches negative 2 of g of x. So notice now all I have to do is evaluate these 2 limits, which can be determined by the graph. So the limit as x approaches negative 2, so there it is there. We see that we're approaching a y value of 0, plus 5 times the limit as g of x approaches negative 2 here, so we can see it's approaching that value of approximately negative 1.5. So we can see that this limit is equivalent to negative 7.5. Let's try the next one. The next one would be equal to the limit as x approaches 1 of f of x times the limit as x approaches 1 of g of x. So we're going to evaluate each of those limits independently. So as x approaches 1 for f of x, that's this point here, and 1 for this one. Oh, look at this one. This one's undefined or does not exist. We have that the first limit approaches a value of 3, but the second limit does not exist. So therefore, this limit does not exist. Next one, what about the limit as x approaches 1 of f of x divided by g of x? Well, that's the limit as x approaches 1 of f of x divided by the limit as x approaches negative 1 of g of x. So let's look for those values. Alright, so x approaches negative 1 for f of x. That's up here, and that's a value of 3. So we end up with 3 over negative 1 here. Would be approaching a value of negative 2. So we end up with negative 3/2 is the limit of f of x divided by g of x. So this is where we're using our limit laws to help us evaluate limits. And finally, example 6. I'm told that the limit as x approaches 0 of f of x over x is equal to 1, and the limit as x approaches 0 of g of x over x is equal to 2. But I want the limit as x approaches 0 of f of x over g of x. So one way to do this one is to just go ahead and divide numerator and denominator by a factor of x. So this gives me the limit as x approaches 0 of f of x over x divided by g of x over x. And using our limit laws, this is the same thing as the limit as x approaches 0 of f of x over x divided by the limit as x approaches 0 of g of x over x. And notice we have those limits up here. So now we're going to sub those in. And for the first limit we get 1, the second one we get 2, and there is our answer. The limit as x approaches 0 of f of x over g of x is equal to 1/2. Try the following questions and give me a shout if you need some help.